Hi, I'm Anthony Yeates. I'm a lecturer in mathematics at Durham University, and in this video I'm going to talk about the scalar product between vectors. So I'm going to look at how it's defined, how we can calculate it, and then how mathematicians might think about generalizing it, and that's the kind of thing that you'll see if you take maths at university. So we're going to take two vectors, A and B, and I'm just going to assume that they're in 2 dimensions so I can draw it on the board easily. And what we can think of, or what we can ask, is how much of B is pointing along A? So in the sort of jargon, we would say, what is the projection of B onto the vector A? So what we do is we drop a perpendicular from B to A with a right angle, and the projection is then the length from B up to A. And this length I will call x. And if we know some trigonometry, and we know the angle between A and B, so we'll call that theta, then we can just calculate what this length x is. So you should know that cos of theta is going to be, well, the adjacent side, length of the adjacent side over the length of the hypotenuse of this right-angled triangle. The adjacent side in this case is x, and the hypotenuse is the length of the vector B, and which I'm going to call B without an arrow on top, by which I mean the length of vector B. So we can just rearrange this equation, and we find that the projection of B on A is B cos theta. Now we can do exactly the same trick and calculate the projection of A onto B. So we drop a perpendicular from A to B. It's slightly longer than the vector B. And then the length we're interested in goes from here to the origin, and I'll call that y. And we can calculate this y also in the same way. And in fact, we'll get that y is equal to A cos theta. So the projection of A on B is A cos theta. Now, what we could ask is, can we make a sort of symmetric measure that tells us how much these two vectors point in the same direction as each other? And that's what we call the scalar product. So we write it as A dot B, and it's defined to be AB cos theta. So it's similar in spirit to these projections of one on the other, but it doesn't matter which way round you do it, it's the same. So sometimes this is called the dot product, just because of the notation that people use for it. But the scalar product is probably a better name to remember, because it tells you that the answer is a scalar as opposed to a vector. Right, so this measure tells us how much they point along each other. It doesn't have a natural direction associated with it. It's a scalar. So to make it clear exactly what this is, it's good to look at some special cases. The first special case is where A and B point in exactly the same direction. So A, here's my origin, A comes up to here, and B is pointing in the same direction, although it's a different length. So in this case, my angle theta is equal to 0. And hopefully everyone remembers that cos of 0 is just 1. So therefore, in this situation, A dot B is equal just to AB, the lengths of the vectors multiplied together. On the other hand, it could be that the two vectors A and B point in exactly opposite directions. So A coming up here, B in the exact opposite direction. This is what we would call anti-parallel. So in this case, the angle between them is pi, or 180 degrees, if you like. And we know that cos of pi is -1. So A dot B, in this case, is minus AB. So it has the same magnitude but opposite sign. The third case I want to show is if the two vectors make an angle of 90 degrees with each other. So suppose this angle here, theta, is a right angle, or in other words, theta is pi by 2, 90 degrees. Well, cos of pi by 2 is 0. So in this case, A dot B will be 0. So you can see that the maximum possible value this thing can be is when the vectors point in the same direction, or with a minus sign when they point in the opposite direction. Every other direction will be somewhere in between because the cosine will be less than 1 in magnitude. And if they point exactly perpendicular to each other, then we get 0 for this measure. So they don't point in the same direction at all in this case. So that's consistent with what we want this to be. And we have a name for this third case. The vectors are called orthogonal. Just means that they're at right angles, essentially. So now I want to show you an example of where the scalar product very naturally arises in a physical problem, or maybe a mechanics problem, you might think of it as. So I've got a little picture here. This is me pulling along a concrete block along the ground. So I'm exerting a force on the block from my arm, and we'll assume that this force is in an angle, or makes an angle theta with the horizontal, with the ground. And the block is going to move horizontally because it's not going to lift up as a result of this. And I'm going to assume that I move it a distance d. And we can think of this d as being a vector going along the ground. Where this comes in is, if we want to calculate the amount of work that I do in moving the block this distance d. So how much energy goes into this. And the formula for the amount of work done is the force in the direction of motion multiplied by the distance that you move the object. So that's the work you do on the object. Well, what's this? The force in the direction of motion is exactly the component of F in the horizontal direction. If you like, it's the projection of F on the horizontal direction. And we saw just in the previous picture that that's the magnitude of F times cos theta. The distance moved is very simple. It's just the length of my vector d. So it's just d. Maybe we put some brackets around here. But this is exactly the scalar product between F vector and vector d. So this is a very natural example where the scalar product comes in. And one thing you can see, for example, is I'm going to do the maximum work on the block for the same amount of force if I pull it horizontally, because then theta will be 0, cos theta will be 1, and all of the magnitude of my force will be going into moving the block. I won't be wasting any in the vertical direction where it doesn't do anything. Okay, so we've seen an example of where you might see the scalar product in practice. But when you're doing practical problems, it's useful to have a different way of writing vectors. And this is expressing them in terms of components in the coordinate directions. So you probably will know that you can, in this two-dimensional picture, your vector A, you might write as a component in the x direction and a component in the y direction. Alternatively, you might use the notation ax times some unit vector I, ay times j. So I and j are just unit vectors in the coordinate directions, so vectors of length 1. And you should be familiar with this notation. We can do obviously the same for vector b. So vector b will be bx I plus by j. And the question is, what's the scalar product in terms of these components? Well, let's start from the definition. A dot b is equal to ab cos theta. And remember, theta is the angle between A and B. So if you like, this angle. And I've drawn on here theta A and theta B, which are just the angle between the x-axis and vectors A and B. So that means I can rewrite this as AB cos theta B minus theta A. Now, if you remember your trig identities, you'll know that the cos of theta B minus theta A can be rewritten in another way. In particular, cos theta B cos theta A plus sine theta B sine theta A. It's important to get the sign right. So now I can expand out this product and write it in a slightly different form. I'm going to write A cos theta A times B cos theta B. This is just exactly the same. Plus A sine theta A times B sine theta B. And I'm actually almost there, because if you think about what is A cos theta A, if you remember back to our projections, it's going to be the distance x along here, so the x component of A. B cos theta B is going to be the x component of B. On the other hand, the A sine theta A is going to be the y component of A, and this is going to be the y component of B. So what we get is, if I move up here, A dot B is equal to AX BX plus AY BY. So it's very easy to calculate the scalar product in terms of the components of the vectors. Now there's another upshot of this, and that is that if we can calculate the scalar product like this, then we can rearrange the formula and calculate the angle theta from the components. So we can say that cos theta, if we rearrange our formula over there, is A dot B over AB. And then we could take the inverse cos to find the angle. And this A dot B, we know we can write as AX BX plus AY BY. And then the magnitude of A in terms of components, we just use Pythagoras' theorem, AX squared plus BX squared, and then we square root. So we've got A square root of AX squared plus ay squared, and then the same for the magnitude of b. Bx squared plus by squared. So this gives us a formula for the angle if we know the components of the two vectors. And this is very useful in practice as well.